Hello. In this fourth lecture on PIC microcontroller 16F877, I am going to discuss a special functional block of this device which is called as the CCP module. It is compare, capture and PWM module available in this device. This is actually the special feature of PIC microcontrollers. It is provided typically for some industrial applications like generation of different kinds of waveforms, periodic pulses, pulse width measurement, or maybe for generation of PWM, pulse width modulated signal, maybe for the purpose of DC power control supplied to the DC loads. In this particular lecture, we'll be discussing the compare mode of operation and capture mode of operation in quite details.
Okay, so in this chapter, which is chapter 11 from this unit, chapter 11 of ABG, we are going to discuss CCP models. And second, the ADC, A to D converter model in this microcontroller. Okay, so let's begin with the first one, CCP model. Okay, if you consider the pin signals, then here you can see that there are certain input alternate functions to the input pins. Okay, for example, here you see the port C pins RC1 and RC2 have alternate functions like CCP1 and CCP2. Okay, so these are the input pins for input or output pins for the CCP models. Actually, there are two CCP models inside this. Okay, so here you see that there are two such input pins. Okay, so there are two CCP modules in this microcontroller. Two CCP modules in this microcontroller, maybe CCP1 compare, capture and PWM module 1 and CCP2, two identical modules. Okay, and these are the pins associated with the two modules. CCP1 is connected to this and CCP2 is connected to this. Okay, so these are the pins corresponding to this. Okay, so let us study these modules and how they work and what are the different modes of operation. Okay, actually each module, see, both are identical modules. Whatever we discuss for one module is applicable to the other module also. Each module can operate in three different modes of operation, and those modes are compare mode, capture mode and PWM mode, or capture, compare, PWM mode. Okay, so let us discuss the operation of this module in each of this mode one by one. Okay. Okay, so let us begin with the capture mode. capture mode of operation. So this shows the block diagram, and there is a control registers that is called as CCP1 control and CCP2 control. These are control registers. Okay, so wait a minute, I will show you. Okay, so let us first of all discuss the capture mode of operation. We are discussing CCP modules. CCP module can be denoted as CCP-X module. Okay, X may be either 1 or 0, so it means either CCP1 or CCP2. Okay, the discussion is applicable to any one of the two. Okay. So first of all, we are going to study the capture mode of operation. Capture mode. Okay. Actually, each of this module has a count register, and that count register is CCP R1H and CCP R1L. Okay, so this is for CCP1. Okay, suppose we discuss it for CCP1. Same thing is applicable to CCP2 also. So this is actually a 16. There are two 8-bit registers like this. So this can be called as the count registers. So these are count registers. So each of this module contains these two count registers. Each register is 8-bit. So total 16-bit. Okay, one more thing, that each of this module has a control register that is denoted by CCP1 con register. Okay, control register. So this is an 8-bit register. You have to adjust the bit pattern in order to set the mode of operation of this particular module. Okay, then these modules, or these two modules, they occasionally use, or they use basically timer 1. They use timer 1 for their operation by default. We have discussed that there are 3 timers in this PIC microcontroller: timer 0, 1 and 2. Timer 1 is a 16-bit timer, you know. It's a 16-bit timer with pre and post scaling. Pre-scaling and post-scaling. Okay, post-scaling. Okay, so that timer is used by default by these modules when you use these modules. Okay, and there is the last mode of operation is PWM mode of operation. You know, capture, compare, and PWM. So in the PWM mode of operation, it uses timer 2. Timer 2 is used particularly in PWM mode of operation. Okay, that timer is 8-bit timer. Okay, so it means that if you are operating this mode, this particular module in say capture mode or compare mode, it will use timer 1. So timer 1 is used for operation in capture mode or compare mode. Okay, and when you operate this particular module in PWM mode, then it uses timer 2. Okay, so that is the default use of timers. Okay, so that is how the different registers are there, and we will discuss with help of these registers how this particular mode or that module operates in a given mode. Okay, now let us go back to the functional block diagram for capture mode. The operation of the capture operation of the module in the capture mode is shown here. You can see that these are the count registers. Just now we have mentioned them. So this is the diagram shows as an example the operation of CCP1 module. CCP1 module. So same thing will be applicable to CCP2 also. Okay. So for CCP1 module, these are the count registers. We have seen that. These are count registers. So total it is 16-bit count register. Okay. Now this is the 16-bit count register of timer 1. So this is the count register of timer 1. So when you are operating this module in capture mode, the timer 1 will be used by default. The operation is simply like this. You know, just now we have seen that there is a pin associated with this module. CCP1 is the function of the pin, which is alternate function on port C pin RC2. Okay, so when you are using this module, this pin will act as input pin. Here you may supply some pulses, train of pulses, or maybe a TTL waveform like this. Okay. Now there is a prescaler. This is a prescaler. It is not the prescaler of the timer. Timer has different prescaler. This is the prescaler of this CCP module. It divides this frequency or these pulses, number of pulses per second, either by 1 or 4 or 16. Okay. So what happens is like this. When your timer will be operated in the free running mode. Okay, suppose initially you load the timer by count say 0000 and you start the timer. Then the timer will start running and the count will go on incrementing like this, so on. Now at the instant age of this signal occurs, then the count in the timer count registers will be copied into the count registers of this CCP module. Okay, so that's why this is called as capture mode of operation. Okay, at the rising age of the input waveform, for example, the count in the timer registers will be captured into the count registers of the CCP module. At the same time, there is an interrupt flag associated with this CCP module. That flag will set. Okay, and if the interrupt is enabled, corresponding interrupt is enabled, then the CPU will be interrupted. So when the CPU is interrupted, the CPU can read the content of these registers. Okay, so it will find the count which is captured here. So this will happen maybe at every rising age. If the prescaler is 1, or it may happen at every 4th rising age. This is 2nd, this is 3rd, and this is 4th. So every 4th rising age. So if the prescaler is selected to be 4, okay, or it will happen at every 16th rising age. 16th rising age, right? If the prescaler is 16. Okay, also it is possible that this count can be recorded or it can be captured maybe at falling age. Instead of rising age, you can program this module to capture the count at falling age. So it may be every falling age, or every 4th falling age, or every 16th falling age. Okay, all this setting is done by using that CCP-con register, CCP1 control register. Okay, we'll see the bit pattern of this. So with help of the bit pattern, you can set the required mode of operation, and depending upon that, it will be captured either at every age, or 4th age, or every 16th age. Is it clear? So that is the capture mode of operation. Okay, so if you go for the CCP1 register or CCP2 control register, CCP1 control or CCP2 control register, both have identical bit pattern. Okay, this register is a control register used to configure the module. So you can see the meanings of the different bits. If you consider these bits, mode set bits, right? It is CCP X M3 to CCP X M0. These are mode set bits. Okay, their meaning is given here. So mainly this register contains the 4 mode set bits. Okay, with help of these bits, you can select one of the mode of operation for the given CCP module. For example, when all these bits are 0, the CCP module will be turned off. As I told you that this facility is provided everywhere in this microcontroller, that whenever you don't need to use any functional block, that block can be kept switched off. That reduces the power consumption. Okay, now when you want to use this module, then there are different options available. Either you can operate this module in the capture mode, or you can operate that into the compare mode. There are these various options for the compare mode, or you can operate it in PWM mode. Okay, so these are the CCP modes of operation: capture, compare, and PWM. Okay, so in the capture mode, right now we are discussing this capture mode. So in the capture mode, you can see the various options available here. Okay, the count can be captured at every falling edge, or it can be captured at every rising edge, or every 4th rising edge, or every 16th rising edge. So these 4 options are available. They can be selected with help of these bits. Is it clear?
Yes, sir.
Okay. So that's how the this will work. The capture mode of operation will operate. So we have seen this block diagram. So whatever signal you supply from outside, at every maybe falling edge or rising edge, the count will be captured into the count register, and the CPU will be interrupted. You can understand that this typical thing can be used, for example, to measure the period of the input waveform. Okay, for example, if you select the option of every rising edge, or maybe every, suppose you select the option of every rising edge, then your the count will be captured at every rising edge of the input waveform. Suppose this is your input waveform. Then at every rising edge, the count will be captured, and the CPU will be interrupted. So what you can do, that you can start your timer 1. You can start your timer with initial count to be 0, 0, 0, 0. So that count will go on incrementing. It will increment depending upon the CPU clock. It's quite high as compared to the input signal that you are applying. Okay, so when it comes here, at this instant, the count will be latched, n will be latched. Okay, so that n will be available in the CCP registers. So this will now contain n. Okay, so this n will depend upon the period. Right. So if you know this clock frequency, suppose this clock frequency is 1 megahertz, for example, then the period of this will be 1 microsecond. Okay, and therefore the count is incrementing after every 1 microsecond, right? And if this n comes out to be suppose 1000, then it means 1000 into 1 microsecond is the period, say 1 millisecond. Okay, so so that's how we can measure the period of the input waveform. If you want better resolution, you can latch the count after say every 4th or 16th rising age. So in that case, you start your timer, and after 16th rising age, at the 16th rising age, for example, the count will be latched. Okay, so you can take the difference or this count and this count. So this count will tell you the total time interval for 16 clock cycles. 16 cycles of this. Okay, so whatever count you get, n, that should be divided by 16. That will give you n corresponding to the time period. Okay, so from that you can calculate the time period of this waveform. Is it clear?
हॅलो सर.
हाँ बोला.
एकदा ते कॅप्चर केला अकाउंट आणि इंटरप्ट जनरेट झाला.
हो.
नंतर दुसऱ्या वेळी परत रिसेट होतं टायमर किती पुन्हा पुढे.
हाँ बरोबर. ऑटोमॅटिकली रिसेट होत नाही. पण when you go to ISR, let's see when it is interrupted here, for example when it is interrupted here, right? In the ISR you can reload the count to 0. You can reset the count in the timer to 0 and restart the timer. Okay, so that the next time again that count will be captured. Again it will be starting from that difference will be dependent upon this time interval. Automatically reset होत नाही. बोल. Okay, automatically reset होत नाही. You have to reset it. Okay, or what you can do that your timer may keep on working continuously. Okay, and after every rising age, suppose you record the count. After every rise, say n1 here, then here you get n2, right? Here you get n3, suppose. Okay, then we can understand that you can obtain this time interval by taking difference. Okay, n3 minus n2 will give you the count n, which is proportional to this time interval period. Okay, because your count is your timer is up counter. Okay, so n3 minus n2 will give you the period. Okay, so that's how also you can determine the time interval. Okay, it is also possible that you can measure the pulse width. For example, suppose you are receiving a pulse only. You are not receiving continuous train of pulses, but single pulse is being received on your input pin. Suppose this is the input pin. I think it is RC RC2 CCP1. RC2 CCP1. Okay, suppose this pulse is being received and you want to measure the pulse width. Okay, it is possible. What you can do? You can start the timer. Somewhere here. You can start the timer. So timer will be started from here 0 0 0 0. It will go on working. Initially, you set the module to respond to the rising age. So at the first rising age, the count will be captured, say n1. Okay, and this will go to the ISR. Okay, here the interrupt will be generated. So in the ISR, you can change the sensitivity from rising age to falling age. So now in this interval, it is sensitive to the falling age. So as soon as the next falling age comes, again the count will be captured. Okay, so now you can obtain the difference n2 minus n1. So that difference will be proportional to the width of this pulse. Okay, so that's how we can manage to measure the pulse width. Is it clear?
Yes, sir.
Okay. So this we have discussed. So I think this is clear about your CCP module operating in the capture mode of operation. Okay, then we have seen the CCP control register. There are mainly these 4 bits. These 4 bits are used to set the mode of operation. These 2 bits we will discuss later. They are associated with the PWM mode of operation. Okay, when we discuss that time we will discuss this. Okay, so once you understood this, then let's see how to write a program to use the CCP module. Okay, so suppose you want to write a program to use, say, CCP1 module, say in capture mode. Okay, then the program will have to do these steps. You have to set the port bit RC2 as input bit. Okay, because on that particular port pin you are going to receive the external signal, right? External signal. So that RC2 pin, which has alternate function of CCP1 input, that should be configured as input pin. Okay, so that can be done by using TRISC register, you know that. Okay, next you have to put proper bit pattern in CCP control register. Okay, just now we have seen that CCP control register, you have to put proper bit pattern to select the capture mode of operation. Say for example, every rising edge option, every rising edge suppose you want. Okay, then you have to enable the interrupts. Now to enable the CCP interrupt, you have to go through 3 steps. Right. One is that you have to enable the CCP interrupt enable bit. You have to set the CCP interrupt enable bit, which is in peripheral interrupt enable register. Then in the interrupt control register, these 2 bits are there which should be set. Okay, one bit is the peripheral interrupt enable bit. It enables or disables all the peripheral interrupts at once. And another bit is the global interrupt bit, which enables or disables all the interrupts at once. Last time we have discussed this in details, that interrupt control register contains these 2 bits, and the interrupt enable bits and flag bits for all the peripheral interrupts, right? They are available in the peripheral interrupt enable registers and peripheral interrupt registers. Okay, so therefore to enable the interrupt, CCP1 for example interrupt, you have to set the CCP1 interrupt enable bit in this register, and then you have to set this bit as well as this bit in the interrupt control register. Okay, I think this we have discussed last time. Suppose I go back to another. So here we have seen those peripheral interrupt and right. So in the interrupt control register, basically in the interrupt control register, I don't know where it is, interrupt control register. Yeah, option register. So ठीक. So this is the interrupt control register. You have seen that interrupt control register contains these 2 flags, global interrupt enable and peripheral interrupt enable. Okay, because your CCP module is coming under peripheral interrupt. The interrupt of this module coming under, it comes under the peripheral interrupt. So these two bits should be set from the interrupt control register. These two registers. GIE, global interrupt enable, and peripheral interrupt enable. And then when you go to the peripheral interrupt register, there are two peripheral interrupt registers, PIE1 register and then PIE2 register. PIE2 register. Okay, so here you can see the interrupt enable bits for CCP. So CCP1 interrupt enable. Okay, here it is CCP2 interrupt enable. Okay, so these respective bits should be set in order to enable the CCP interrupt. Okay, also the interrupt flags of CCP modules are available in these PIR registers. So PIR1 and PIR2. So here you can see the CCP2 interrupt flag bit, and here it is CCP1 interrupt flag bit. Okay, so these are all available in the these registers. Okay, so that's how this thing bit should be set. So in order to enable the interrupts. Okay, then you have to set the timer. You have to operate. You have to start the timer. Timer 1 particularly by loading initial count, say 00, 00. You have to. Okay, then you have to enable the timer. You have to start the timer. In short, start timer. Okay, so that's what you have done. You have configured port C pin as input pin. Then you have put the bit pattern in the CCP control register to configure the CCP module to operate in the capture mode. Then you have enabled the interrupts. Then you have started configured the timer and then started the timer. Okay, then your main program is over. Now what will happen? Because you have selected every rising edge option, when the first rising edge comes of the input signal, the CPU will be interrupted, and that is the interrupt due to capture module, capture mode of operation. So in the actually the two things will happen. At the rising edge, the count, whatever is the count in the capture registers, that count in the timer registers, that will be captured into the CCP registers. So that count will be captured. Okay, and the interrupt will be generated. When the interrupt is generated, the flag is also set. So in the interrupt routine, first of all, you can reset the flag manually. Okay, then you can restart your timer, as I told you a little before, that whatever count is recorded in the CCP registers, that you can use for your calculations. But at the same time, now you can restart your timer. Timer can be restarted back to 0. So again, the next new counting will start. Okay, and then return. Okay, so in the ISR, you get a count in the CCP registers. So CCP R1H and CCP R1 lower. Okay, so whatever count is there in this register, that count will tell you it will give you the current count. Okay, so next time the interrupt occurs, whatever count you get, that count you can compare with this, and from that you can determine the period. Is it clear?
Yes, sir.
Okay. Yes, sir. So let's continue. Okay, so this is the program which is written in your book. I have given you the flowchart. I will share you this flowchart next through the classroom. So this is a flowchart written for this program. This program is given in your book. You can just compare this program with the flowchart. You know the instructions of this PIC microcontroller, and you know how to write the program. So just compare this with the flowchart. So if you know the flowchart, then you can write the instructions. So this is the program for initializing CCP1 module in capture mode of operation. So these are some initializations, definitions of the different variables. This is for the assembler. Okay, so these are the addresses of the different registers. For example, PIE1 equate 8C, PIR1 equate 0C. So these are the addresses of these registers. Okay, actual program will start from here, ORG0. You have written program for PIC microcontrollers last semester. Okay, go to start. Okay, and then when your actual program begins, you can see that initially your timer registers are reset. Okay, so you are loading 0000 in the timer registers. TMR1H and L. Okay, then you are putting proper. Okay, you are using TRISC register, right, to configure the pin as input pin, right, bit set file TRISC RC2. So what is done here is the RC2 bit of port 2 is configured as input bit, you know, the operation function of TRISC register. Okay, then what you are taking this pattern in W, move literal W, and then you are loading that pattern into CCP1 con register. Okay, you are changing this bank appropriately, you know, just to when the register is in the given bank, you have to shift to that bank that you know. So this pattern is loaded in CCP1 control register. You can check this pattern with the format of CCP control register, right? Okay, then the timer 1, and so this is the pattern which is loaded in the timer 1 control register. Okay, so it enables the timer 1, uses the internal clock option. You know, timer can be operated as timer or counter. So internal clock is selected, so it will be operated as timer, and the timer oscillator option is enabled. Okay, so that is loading proper bit pattern in the timer control register. Okay, then you have to enable the interrupt. So this is for timer, then you have to enable the interrupt. Okay, so for that you have to enable this bit, you have to set this bit, peripheral interrupt enable register matlab bit hai CCP1 interrupt enable. Then you have to set two bits, which is peripheral interrupt enable bit and global interrupt enable bit in the interrupt control registers. Okay, so that is enabling of the interrupt. Okay, so CCP1 interrupt is enabled. Okay, and then the program remains in this loop. Okay, that means the job of the main program is over. So when the interrupt comes, as you have seen that whenever the edge occurs, at the rising edge, the interrupt will occur and execution will be transferred here. Okay, so here we have seen that the count will be loaded into the CCP1 count registers and the interrupt flag will be set. So what you are doing here is that you are resetting the interrupt flag. Okay, it is the CCP1 interrupt flag in PIR register. So that has to be reset for the next operation. Then again you clear the contents of timer registers so that your timer can be restarted from 0000 like this. Okay, and return. Okay, so this is a return from interrupt routine by enabling the interrupt. You know this instruction. So this returns back to the main program. Okay, so once again the process will continue. Once again, when the next edge comes, next rising edge comes, at that rising edge again the interrupt will occur. Again the same thing will be repeated. So this is how we can write a program. So if you are asked to write a program in a theory paper, you may not write all these details. Okay, this part may not be written because this is needed only particularly when you have to execute the program practically. So this part may be omitted. You can start writing your program from this org00. Okay, so this onwards you can write your program, basic initialization, and then enabling the interrupt. Is it clear?
Yes, sir.
Okay. Now let's go ahead. Next mode of operation is compare mode. Once again, the same hardware is available. You have the compare mode also uses the timer section, timer 1. These are the timer 1 count registers, and these are the CCP module count registers. Okay, it also uses a pin corresponding to that CCP module, RC2, for example, CCP1 pin. Now this pin has to be configured as output pin. The operation is simply like this. You have to load some initial count. You have to load some count in CCP count register. Suppose you load the count, say n, and then you start your timer maybe from 0000. Okay, so timer will start working. Timer will start working. When this count in the timer, it is compared. It is compared with this count. So when it becomes equal to n, so timer count, when it becomes equal to n, there is a change in the status of output pin. Okay, that means the output pin may go from low to high, or it may go from high to low, depending upon the programming. So there is a change in the status of the output pin, and at the same time the interrupt flag is set and the interrupt is generated. Okay, so every time the count matches with the count in the timer registers, it matches with the count in the CCP module count registers, an interrupt is generated. Okay, and there is a change in the status of the output pin. That's all. So this is the working of the CCP module in compare mode of operation. Now there are various possibilities when operating in the compare mode. So for that you may check the bit pattern for CCP control register. In the CCP control register, there are various options available for compare mode. You can see these are the various options available for compare mode. Okay, so depending upon this, the CCP module will work in the compare mode. So for example, you can select this option. For example, compare mode, set the output on match and set this interrupt flag bit. So interrupt flag will be set when match occurs. At the same time, the output will be set. That means the output bit RC2 CCP1 bit, okay, RC2 CCP1 bit, that will set. Set means it will go from low to high. Or it is possible that you can select this option that everything is same as before, only thing is that output will be cleared. In that case, the output will go from high to low. Okay, in the previous case it was going from low to high. Okay, so in any case the output makes a change. It may change from low to high or high to low. Okay. Now there is a third option available, compare mode. Generate a software interrupt on match. That means the flag bit will set as usual. So flag bit is setting every time, and the interrupt is generated. But in this particular option, the pin status will remain unaffected. There will be no change in the status of the pin. Okay, only if you select this option, when the match occurs, when the timer count matches with the CCP count, the interrupt flag will be set and interrupt will be generated. So you can understand that these modes are available for introducing certain delays, generating certain delays, right? You can start your timer from 0 and you can load some count in the CCP count register, right? So that count has to be adjusted such that appropriate delay will be generated. That means there will be change in the status of the output pin after the required amount of delay, right? So larger the count in the CCP register, larger will be the delay, that you understand. Okay, so this can be used to trigger a event, certain event, maybe at the output pin, or maybe it can be used to generate an interrupt or interrupt the processor after a certain delay, So you are starting your timer from 0 and you are putting some count n in the CCP register. So as you change this n, maybe smaller or larger, the delay from this point will change. Okay, so that means you understand that depending upon this count, some event at the output is going to be triggered after certain amount of delay, depending upon this count, or your CPU is going to get interrupted after certain amount of delay. Okay, so that delay is adjustable with help of this n. Okay, so that's the basic purpose of this compare mode of operation. One more option can be seen here in the compare mode of operation. The option which is available, which is seen here as the last option. Here, this in this option, some special event is triggered. Of course, the flag is set. That means interrupt flag is set, but the pin is not affected. So it is same as this. The pin is not affected. There is no change in the status of the pin, but the flag is set. The flag is set. CPU is interrupted. Okay, and in this option, it starts the A to D conversion. Okay, and one more thing which occurs here is that the timer 1 is it is reset automatically. So that means this particular mode, this particular option can be used to trigger the A to D conversion after a definite interval of time repeatedly. Okay, so that means what is going to happen, that you have loaded some count n in the CCP count register. So when that timer count matches with that, your A to D conversion will be started. Okay, and it will reset the timer 1 automatically, so that the counting of the timer will be restarted. Okay, the A to D conversion will give some result after some time interval. Okay, meanwhile the timer has been started. So when the timer count again matches next time with the count of the CCP module, then again the A to D conversion will be started. Okay, so this particular option can be used to trigger A to D conversion after every definite time interval repeatedly. You can understand this. Okay, for example, here you have started, suppose initially you make your count in the timer count, initially suppose it is made 0. Okay, and you have set some count n in the CCP module. Then what will happen when this matches? Suppose it matches here, it matches with this count. So when this becomes equal to n, you know the interrupt will be generated and A to D conversion will be started. Start A to D conversion. Okay. Again, at the same instant of time, this count will be automatically, timer count will be reset to 0000 automatically, and again the operation will continue. Okay, the timer count will go on incrementing. Okay, again when it matches with n after same time interval, once again the same thing will happen. The A to D conversion will be started. So that is how it goes on. Okay, when the A to D conversion is started, after a certain duration, you know, depending upon the conversion time of the ADC, the conversion will be over and the data will be ready. So end of conversion will be seen somewhere here, and you can get the data. But next time the conversion will be started after definite time interval. After definite time interval. That is the importance of this use of this particular module along with your ADC. Okay, so what we are doing here is that you are sampling the analog input by converting it into digital equivalent after every definite time interval. That is important. Okay, depending upon the type of the ADC, it may take shorter or longer time to convert to complete the conversion. Okay, so it may be here it may be available in a shorter time, here it may be available in a longer time, maybe. Okay, but that will not affect the duration between two samplings of the ADC. Okay, so that's the advantage of this last mode of operation in compare mode. Is it clear?
Yes, sir.
Okay. So now you can see how to write a program for that compare mode of operation. So this is a program for this. Okay, what you need to do when you want to operate your module in the compare mode, first of all you have to configure this pin as output pin first of all. Then you have to initialize your timer with proper 0 count, and you have to start the timer. Then you have to load some initial count n in the CCP registers. You have to enable the interrupts. Okay, and then the process will begin. So this shows the programming steps. Number 1, your port C pin should be configured as output pin. Okay, then you select the mode of operation of the CCP module by loading proper bit pattern in CCP1 control register. You have to operate this in compare mode. Okay, then you have to load proper word in the count register of the CCP module. Okay, which will decide the time interval between two successive samplings. Okay, then you have to enable the interrupts as the same process as we have seen last time. You have to enable, you have to set the bit CCP1 interrupt enable bit in PIE register, then these 2 bits in interrupt control register. Then you initialize your timer with 0 count. So timer 1 lower, higher, both should be loaded with 0. So initially 0 0 0 0 will be loaded into the timer 1, and you have to start the timer. Okay, then this basic setting is done. Then what will happen when that particular timer count will go on incrementing, and when it matches with n, whatever n you have loaded here, when it matches with n, interrupt will be generated. Okay, so in that interrupt routine you can reset the interrupt flag, right? You can restart your timer if you want. Okay, and clear the port bit. Suppose you have selected the option that upon interrupt the port bit should be set. Then when the interrupt occurs, when you go to the interrupt routine, you can reset the bit once again back, so that the next time when the interrupt occurs, again the bit can set. So you have to clear the port bit and then return. So because of this, what will happen here, you can see that this is the status of the port pin. Initially your timer has 0 count, right? When this matches with your n, the output pin will go high, and it will go to the ISR. So in the ISR you do all this, and again you make the pin low. So a sharp pulse will be generated in short at the pin. Okay, and your timer is restarted. So once again after the same time interval, whatever time interval you have here, after the same time interval again you will get an interrupt, again a pulse will be generated. Okay, so this will keep on happening continuously. So in short, this program will generate a train of pulses with definite duration, right? These pulses can be used externally to trigger certain circuit. Okay, because these pulses are hardware pulses. Okay, they may be given to some circuit, which the circuit can be triggered repeatedly for definite time duration. Okay, so that's the use of CCP module. Again you can see the program. I can compare that program here, org. So here you are, after you start your program, initially you clear the timer registers. So timer register is loaded by 0000. Then you are enabling the interrupt. CCP1 enable bit, PIE bit and GIE bit, these are enabled. So enable. Okay, so interrupt will be enabled. Interrupt enabled. Okay, then clear the bit, TRIS C bit. Port C bit is cleared. So right, so initially it is low. Port C bit. Okay, then you load proper pattern in the CCP-con register. Load some count in CCP RL register. So the count loaded here is 0. So you start your timer from 0. Right, when the timer overflows again from FFFF to 0000, it will match with N. So full time interval is used. Right, and again in the interrupt routine, as we have seen, that you have to reset the output bit, reset the flag, restart the timer, right, clear the output bit. So if the bit is set here, output bit is set here, then it will be cleared in the ISR. Right, you can compare these instructions with the logic with the flowchart. Is it clear?
Yes, sir.
काय शंका असेल तर बोला. So today we have discussed two modes of operation of the CCP module. One is capture mode, another is compare mode. Okay, each mode has some applications, definite applications. Particularly in the industrial scenario, you need this kind of operations.